The glass shard simulation is slightly different than our emitted RBD debris from last week, because in the case of our glass shards here, we have all of the shards that we're scattering before the simulation, rather than emitting them per frame. However, that RBD debris setup from week 6 is still a very helpful starting point to set this up. So let's go into our week 6 debris tests, and we can copy this entire RBD section, and we can also copy some of the source point setup as well, like the randomizers for the normal and scale, and the V modification. So let's copy all of that, and then go back to our window shatter setup. And when you paste in that copied setup, this will automatically link up to our glass shard instances null, since that name matches what this was connected to for that debris example, and it looks like it automatically connected to our scatter as well. Right now we're scattering 55,000 points, so I'm just going to turn this down a little bit while we set up our initial scatter. Let's turn that down to a density of 40 for 25 or 27,000 points instead. And since this all linked up automatically, we can take a look at what our initial scattering looks like. Now this initial scatter looks pretty cool. If we zoom in here, it looks like we have a decent range in sizes of our pieces. We do want a mix of these pretty tiny ones and these fairly large ones, but it looks like the ratio is skewed a bit more toward the large pieces than I would like. We really only want a few of these really large ones mixed in there. So if you go to the randomize for the P scale, we can adjust the custom ramp. And in this case, I'm going to take this second point here and drag that down a bit so that we have fewer of those big pieces in our scatter. So this curve on our P scale ramp is looking pretty good. We have a much nicer distribution of shapes now, and we don't have those large pieces overwhelming that distribution nearly as much as we did before. However, if we look closer at some of those big pieces, it looks like they've gotten pretty thick. And we don't have to have all of our pieces the exact same thickness, but it might be nice to normalize that a bit. So let's add a point wrangle after the randomize for the P scale. So I'll call that wrangle normalize thickness, and then use this bit of vex to vary that thickness based on the P scale. So first, this will use a fit function on that randomized P scale value, so that if the P scale is 0.1, that gets mapped to a thickness of 1, and if the P scale is 0.5, that gets a thickness of 0.1. And that will linearly interpolate in between. And then we're creating a scale vector attribute, and we're just setting that to 1 in x and y, and then we're setting that z scale to the thickness value that we've determined from the P scale. It's important to remember for these copy SOP operations that the P scale attribute is recognized as a float uniform scale, and this vector scale attribute will be that per axis scale on top of that. So now with that extra z-axis scaling applied, you can see that the thickness of the glass shards are much more normalized now. You don't really have those large ones sticking out as being so much more thick than all of these smaller pieces. Maybe the large pieces are looking a little bit too thin, so I'll change that 0.1 to a 0.2 instead. And this will be a good starting point for our rigid body sim. Now in the case of the RBD debris from last week, we had the velocity data from the RBD sim for the initial velocity on the debris pieces. In the case of this glass, we don't have that, so we're just going to set that velocity explicitly. And it's fine to do that on these points and then copy that data over, but I often prefer to do the velocity after the copy SOP. It doesn't make too much of a difference either way, it's just my own personal preference. So I'll drag that randomize for the V underneath our scattered instances. And I'll set the primary initial velocity and that x direction. I'll have that go from 0 to 5. So that will push in this direction away from the building. And then we'll set a little bit of variance on the Y and Z as well. I'll just set those to plus and minus 0.2. I'm also going to increase the angular velocity a bit. Let's set that to 15. And because we're going to base the activation of these glass shards on the active frame attribute that we have on our points, we need to make sure that data is copied across in this copy stamp. So on that copy, under the template point attributes, make sure to include active frame under those set attributes. Now we're also going to make a few changes to the sim attributes wrangle as well. We're going to get rid of this velocity multiplier, we don't need that. And for this unique name, we're going to change that prefix to glass instead of debris. And this currently has the current frame number embedded in that name, and we're going to change that to embed the active frame instead. So we can replace int frame with I at active frame. And then we also need to set the active value on the pieces as well. So we're going to set this integer active attribute equal to this conditional test if frame is greater than or equal to the active frame. So if that's true, that evaluates to 1 and sets the piece to be active. And we also want to optimize the sim a bit and tell it to ignore all the pieces that aren't active yet. So even if the pieces aren't active, then they'll still be considered collider objects by default. But if we set this bullet ignore string, then that will tell the simulation to completely ignore all of those pieces. Don't collide with them or do any other computations related to them. So not only will that be a bit faster, but we'll also avoid colliding with these shards that haven't actually shattered yet. And we can set the bullet ignore attribute to be the inverse of the active value by setting it to 1 minus active. Now we need to make some changes in our DOPNet as well, so let's dive inside there. And the most important change that we need to make is on the RBD-PECT object for the debris. We currently have the creation frame set to $F so that it emits and creates RBD objects on every single frame, but we definitely don't want that since we've scattered all of the glass shards from the very start. So you can right-click that creation frame and revert that to defaults, so that will just set this to the start frame of our simulation. It looks like our start frame here is set to 986, so let's jump out of that DOPNet and set this to our real start frame of 985, and then go back inside. And back on this RBD-PECT object, we also need to turn on this overwrite attributes option. In SOPs, we're changing both the active value and the bullet ignore value, so both of those need to be specified here so that the solver will look up updates to that attribute mid-simulation. We should also make sure that this is set to inherit velocity, which it is, and then we can set up our collider objects. Now this debris setup originally had the colliders wired into the second input of the DOPNet, so we can leave that set up as it is and point this to our proxy geometry from our main RBD sim. So this object merge will point to week 5, post sim tweaks, and out final proxies. Now in this case we don't need this attribute delete, but I am going to delete all of the window frames. The reason for that is because I didn't convex decompose the window frames, so some of those collider objects might be kind of problematic for the glass shard simulation. Now for most of our geometry, the collider shapes match pretty well due to the convex decomposition, but since we didn't decompose these window frames, it's creating these convex hulls around each of those shapes, and it covers up a lot of the actual shatter area. So this could definitely be a problem if that collides with the shards that we're emitting. But thankfully, these window frames are skinny enough that we won't really notice if we don't include them as colliders in the sim. So let's jump out of that DOPNet and then go to our merged in RBDs, and we'll create a blast, drop that in after those RBDs, set the group to name equals star window star, and we'll set the group type to points and make sure that is deleting all of those window frames, and it is, so that's all good. And we also need to add our monster as a collider. You could object merge the monster into this portion of the setup if you want, but I'm just going to go into the DOP.NET and directly reference the monster collider from in here. So we'll create that new RBD packed object. We'll add the monster suffix to that, and then I'll point that SOP path to week 3 monster collider and the out collide null. We'll set this to be a deforming static object. Under bullet data, turn on show guide geometry and create convex hull per set of connected primitives, and we'll merge that in with our other RBD packed objects. And now we can verify that we have our monster collider working in our DOP.NET as well. Now, to make this a bit faster to work with interactively, I'm also going to set the glass shards display to bounding boxes so we can drop in a packed edit just before the simulation and set the display as to bounding box. And before we run the first pass at the sim, I'm going to make one more tweak inside the DOP.NET because I want the glass shards to fall a bit slower than the RBDs. So let's dive inside there, and I'll add a multiplier on the gravity. I'll set that to 0.9 times that default value just to slow it down a little bit. Now we'll turn on show all objects to bring back that monster, and I'll template display our proxies and run a flipbook to see what this looks like. So now our sim and flipbook are finished and things are looking pretty cool. Of course, we can only get a rough idea of what it looks like since the display is in bounding box mode, but it looks like everything is behaving nicely and we have a pretty nice dynamic to the whole sim overall. Now, glass is pretty sensitive to how it's rendered. Once we throw a transparent shader on this, this can look like a lot less material in the render than it does in the viewport. So really, you should render this for those final judgments in terms of the amount of glass, how the size is holding up, and the overall behavior. But so far, we can be reasonably confident that this is looking good. Now we need to make a little change to our instancing setup. In the debris version of this, we were emitting the RBDs, so we didn't have to worry about deleting the points that haven't emitted yet. However, in this case, because we have all the points all the time, we need to clean these up before they've become active. Now, in the copied version of the setup, there's this attribute delete that's cleaning up a lot of the attributes from the RBD sim, because this is coming in with a lot of stuff that we really don't need, but that's also deleting the active frame attribute. So we'll need to add an exception to that. So on this attribute delete, we'll select the active frame from that dropdown and put that caret symbol in front of it so that we preserve that attribute. And then we can do a blast based on that active frame. So right after our caching null, we can drop in a blast SOP and connect that. I'll call this blast inactive, and we'll set the group equal to active frame is greater than the current frame. And for that to work, we'll have to set the group type to points, and if you display that and scrub through your timeline, you can see it's only isolating the points that are currently active. Now right now, our glass shards are kind of blending in with the building and the monster since they're just a flat gray, and to help this stand out a bit in our flipbooks, I'm going to give this a bright white color. So if you drop in a color SOP and connect that to our out instanced RBD debris null, we can display that and switch this to HSV color. And on that V value, we can set this to a value greater than 1. So if you set that to 5, then that'll make this a very, very bright white. You might not need to go quite that high, but this will certainly help the glass to stand out in your flipbooks and make it easier to judge visually. Now after making those changes, you can replace this cache null with an actual file cache, then save that to disk and run a flipbook of your simulation with the actual glass geometry displayed. For my new flipbook, I turned on the full resolution fractured building, and I've also turned on display for the intact windows, and I gave those that same bright white color that we put on the glass. Now in this flipbook, this is probably a little bit heavy. This will be a little bit more subtle in the render with an actual glass shader on all of those shards, but this looks like it's in a pretty good place. In terms of artistic tweaks, I feel like maybe we could go a little bit smaller with some of these glass shards, and it's also worth noting that for this simulation, I turned up the scatter amount by another 50%, and the overall number of glass shards seems like it's working pretty well, but it might look a bit better if they were just a little bit smaller. You could also potentially do a bit more speed limiting so that the glass shards don't fly out quite so far from the building, but some of this dramatic glass flinging action from the monster's head is actually pretty cool. But as cool as that is, it might be a little bit extreme and potentially worth dialing down that motion a little bit.